Welcome to this video on the van der Waals equation, one of the coolest sounding and most complicated looking equations in all of AP Chemistry. But before we actually take a look at what the van der Waals equation is and how to use it, let's just return to the ideal gas law. I've written it for you here, PV equals nRT. And if you've watched the ideal gas law video, you'll remember that we made a couple of assumptions when we used this law to describe different gases. Perhaps the biggest assumption that we made is we said that the identity of the gas, so whether we're using helium or neon or ammonia, the identity of the gas doesn't really matter. So we can have a really big gas or a really small gas, and it's not going to change how we use the ideal gas law. So we consider the volume of gas particles to be negligible. And the reason why we can do that is because generally when we have sort of a big balloon filled with gas molecules, the space between those molecules is so much bigger than the volume of the particles, it's not going to really change our calculation even if we were to take this into account, so we can consider it to be negligible. Similarly, we also said that even though we know that when positively charged gaseous nuclei come into contact with each other, they attract, we know this to happen, we're also going to just not take this into account when we use the ideal gas law. And again, the reason that we can do that is because these gas particles are moving in such a large amount of space at such high speeds relative to their size that even if we were to take this into account under normal conditions, it wouldn't really affect our calculation. And so we can consider these little changes, these little scenarios, to be negligible most of the time. But I've got a question for you, and maybe you can think about it before you move on. What happens to these assumptions? So what happens at conditions of high pressure, really super high pressure, and low volume, tiny volume, like the size of a pea or something like that? If we squished a balloon down to the size of a little pea, what happens under these scenarios? Just to visualize this for you, normally when we talk about gaseous systems, again, we're talking about what we might call macroscopic systems, so really huge containers relative to the size of the particles, etc., etc. We assume these things to be negligible. High pressure and low volume, conversely, is something like this, a really scrunched up balloon where the density of the gas is really high. We've got high density of gas, particles are coming into contact with one another all the time. What happens to these assumptions? Well, I can tell you, first of all, the volume of the gas particles is no longer going to be negligible. The space between them is going to be roughly on the same order of magnitude as the actual size of the particles themselves. How is this going to affect the volume calculation? Well, the volume in our ideal gas law this is going to be smaller than the actual volume of the system. So we can say the volume of the system, so volume will be larger under these non-ideal conditions. And whenever we have conditions at which the ideal gas law breaks down, so conditions of high pressure and low volume, we call those conditions non-ideal. So if the volume of a gas under non-ideal conditions will actually be slightly larger than that which we calculate with the ideal gas law. What about pressure? Well, we said at high density, gas particles are interacting all the time. They're coming into contact with each other much more often than they are when they're in this large, expanded state. And when they come into contact with each other, they're actually going to lose a little bit of energy. They're going to be attracted, and their speeds are going to slightly decrease. That means these gas particles are going to interact or going to bounce against their container with a slightly less energy. So the pressure of an ideal gas, or rather, a non-ideal gas at non-ideal conditions will actually be lower. So pressure will be lower than that which we calculate. But in the real world, not all gases obey the ideal gas law. Non-ideal conditions of high pressure and low volume come up all the time. So we still need a way to account for these, or to negate these assumptions, to actually take into account these phenomena in the ideal gas law. And we do that by correcting the terms for pressure and volume. And I'll briefly do that here. We're not going to go into too much detail because, quite honestly, I don't understand how people derived this equation, but we'll sort of make our best effort with me right here. And so volume will be the first thing we correct. And you remember that we said the volume of a system is actually going to be larger under non-ideal conditions than that which we calculate with the ideal gas law. So first, let's solve the ideal gas law for volume. And so we have V on one side. We're just going to divide PV nRT by P. And so we're going to get V is equal to nRT divided by P. And so we said that the volume is actually going to be larger at non-ideal conditions, so we're going to have to add some term, let's call it x, to this equation to account for this change in volume. What is x? Well, I can tell you that x is going to be in some way proportional to the number of moles of gas that we have. And that makes sense because the more gas particles we have, the more space they're going to take up, and therefore the more volume we're going to need to add to the ideal gas law. The other part of this x term is going to be some constant b, and this varies with the gas we're talking about. So each independent gas is going to have its own b value, and this is always experimentally determined. So we look at different gases, we see essentially this b constant just relates how large gas particles are. And so different gases are going to have different sized nuclei or different sized particles, and therefore we're going to need a constant to account for that difference. It's no longer negligible. And so this is experimentally determined. And a quick note on problem solving: whenever you're solving problems with the van der Waals equation, which is what we're deriving right now, you're going to be given these a and b values. You're never going to have to figure them out for yourself. And so finally we can state this as V, perhaps the V which we would calculate with the ideal gas law. The real volume is equal to nRT over P, this is just the ideal gas law, plus NB. So we've amended the ideal gas law to include a larger volume than we would normally calculate. That's the first correction. The second correction has to do with pressure. And we said that the pressure of a system under non-ideal conditions is lower than we would expect. So if we have the ideal gas law solved for P here, we're going to have to subtract some term, let's call it y for lack of confusion. And this y value I'm going to tell you is going to be proportional to the number of moles of gas, N, divided by the volume of the gas, V. And so we can think about this as the molar density, the moles per unit volume of gas. Why does this make sense? Well, at higher molar densities, so when we have more gas particles in the same area, it's more likely that particles are going to come into contact and attract one another. And the more particles attract one another, the more the pressure is going to decrease, the more energy those particles are going to lose. And I can actually tell you that it's an even stronger relationship than this. Y varies according to the molar density squared. So when the molar density increases by 2, this y value, the amount which we need to correct for pressure, goes up by a factor of 4. And we also have another proportionality constant, A here, which again is experimentally determined and varies with the gas you're working with. And so we can state that P is equal to nRT over V, that's just the ideal gas law again, minus A times N divided by V squared. So that makes sense, but now let's combine these two corrections, and let's actually write the van der Waals equation for the first time. So we're going to call our p-value the p-value which we observe. So that's the actual pressure of the system. So that's just going to be this p here, this corrected p. So the p-value which we observe is going to be equal to nRT from the ideal gas law, divided by V. But remember, over here, we corrected V with this NB term. And so if we subtract this NB term from both sides, we're going to get V minus NB equals nRT over P. And that V minus NB is actually what we're going to put in here. So we're going to account for our corrected volume here in the van der Waals equation with this minus NB term with volume. And then also we're going to subtract this A times quantity N divided by V squared from the right-hand side of the equation to correct the pressure term. So we're going to get minus A times N divided by V squared. So this is one version of the van der Waals equation, but it's not the sort of the version you see most often, or the coolest looking version. And to get that version, we're just going to take this term, bring it to the left-hand side, and then multiply both sides of the equation by this quantity here, V minus NB. And I'll do that for you. So we get P observed, so the pressure which we observe, plus A divided by, or rather times N divided by V quantity squared in that bracket, times quantity V minus NB equals nRT. This, lo and behold, is the van der Waals equation. And you can see it looks kind of like the ideal gas law. We've got P on this side times V on this side equals nRT. But these terms, as we've just said, correct pressure and volume for non-ideal conditions at which the assumptions we make with the ideal gas law break down. And to solve problems with the van der Waals equation, we may do that in a future video. You're literally just going to plug values into this equation to solve, usually for pressure, the observed pressure, observed volume, or temperature. So thank you very much, and I'll see you in the next video.